Lesson 27, resistance. We'll be able to explain the properties of resistance. Now, resistance falls in the last of our three electrical ideas that we talk about. We always talk about three ideas. Those ideas are voltage, current, and then resistance. Now, the reason why we talk about them, and we started off talking about current. The reason I like to talk about current first is because current usually has the closest association to electrons. Current's easy to understand. The electrons moving from one place to another. Now, once you have that understanding of electrons moving from one place to another as current, people ask the question, well, why do electrons move from one place to another? That gives us voltage. That's the push. That's the incentive, the carrot on the stick that makes electrons go, hey, I don't want to be over here. I don't want to be with these other electrons. These other electrons over here, there are just too many electrons over here. I want to get away from these electrons. And he goes, yeah, I want to get out of here. So then you go, well, where do these electrons go that are negatively charged? Well, they want to go to the positive area. And so therefore, that's what drives them. The more positives, the more drive. More negatives, the more drive. The closer they are, the more that they're going to be willing to jump. So yeah, a lot of those things come into place when we talk about voltage. Today we're going to talk about the last ideas. We're going to talk about resistance. Now, resistance is a concept, and yeah, resistance is a new concept. But I'm going to base the reason that we always talk about resistance last, because you really need to understand these two before you can understand, pardon me, what resistance is. So we've also talked about so we talked about voltage in a circuit. We said the voltage is very similar to potential energy. If you drop something, then you're losing energy. But we did spend some time talking about energy specifically, remembering that energy, we came up with two formulas. The first, energy equals VIT, and then the second formula we came up with was power. Power equals VI, and power is measured in watts, and power is just energy per second. So those are the that's what watts are. That's what power is. Now, once we did that, we did some examples, and then that was pretty much the end of the lesson. So today we're going to talk about resistance. In fact, what we're going to talk about is these three topics. Guys, just give me a second. I just got to quickly do something. Sorry. Sorry about that, ladies and gents. These are the three topics we're going to talk about today. Now, today's lesson's a bit weird in that we're doing a lot of little things. Normally I would do, each of these would take its own lesson, but these are all like small. So for example, this one's going to take about maybe, this one's going to take maybe 10 minutes, this one's going to take maybe 10 minutes, and this one's going to take 10 minutes. So it's like, they're all very, very small. So I thought I'm just going to cram them all into one lesson. So they don't all fit very well, but once we've talked about this, we're pretty much almost finished the first half of this topic. The first half of this topic is to go through the basics of electricity, not even to talk about circuits at all. And that's what we're trying to do, is just go through the basics of electricity. And then we're going to go through the circuit part second. So then that's what it means is that by the end, when we look at a test, it's like more than half of it shouldn't have any circuits in it whatsoever. Let's talk about this first one, EMF. So EMF, or electromotive force, is a push given to electrons in a circuit by a battery or voltage supply. Okay? It is the amount of energy given to each coulomb of charge. It is measured in volts, not newtons. Now, the reason that I say this is because people always point out very quickly that voltage, even though it's called electromotive force, it's not actually a force. So therefore, it's not measured in newtons, it's measured in volts. We use this curly brackets here, this curly equals E, sorry, to represent electromotive force. In this case, we can see the electromotive force is the amount times the amount of coulombs, times, so therefore the energy per coulomb times the amount of coulombs will give you the amount of energy. Now this is very, very similar, pretty much, no, it's not very similar, it's identical to this formula here. The only difference is instead of V, we're using the electromotive force. Power equals electromotive force times the current. This is similar here, but instead of V, we're using the symbol I. We're using the electromotive force symbol. Now, you might ask the question, why am I teaching you this when I've just showed you these formulas already? And you know what? I asked the same damn question. I looked at this in the textbook and I'm like, okay, electromotive force, yeah, I've heard of that before. What's the big deal? And then I saw these two equations, like, well, I've just taught these two equations. And I thought, do I need to teach this? And I thought, yeah, I probably need to explain this, because the main idea that I think that is important for this is this. We use V or volts or voltage when we talk about components in a circuit. So if I say, how many volts did I drop over a light bulb? How many volts pass through this resistor? How many volts go through this wire in the circuit? That's when we would use the word volts, voltage. But I think when we're talking about specifically the battery or the voltage supply, and I've been looking at a bunch of questions online, and whenever you're talking about the battery or the voltage supply, that's when you use EMF. Because ultimately EMF, a voltage created by a battery, the force that the battery has to push those electrons, that's where that has a specific E, a specific electromagnetic motive force. So yeah, I don't like when they do something like this, when they bring in a new term just for the sake of it. And that's what I feel like they've done here, is they're bringing this electromagnetic force as just a new term for, you know, oh, it's just the voltage, but it's only the voltage that happens in the battery. I don't like it, but I just thought I should explain it to you so you guys don't see this later on and be like, whoa, 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 what's going on? I've never seen this before. Ultimately, you can just use any formula that has V in it, the voltage, and then, you know, any formula that has V in it and the voltage, and just replace it. So we could even do a formula like this. We could say E equals the electromotive force, because I'm going to write VIT. So the electromotive force, VIT. So then that would be a formula to say how much energy is given to the coulombs of charge in a certain amount of time, or something like that. And so yeah, all these formulas are the same. All you're just doing is replacing the V with the electromotive force. I know this is a bit silly, but a bit weird, but does that make sense to people? Can I just get like someone in chat? Does that sort of make sense? Also, if you want to say out loud, you can, how stupid this idea is, or maybe you think, no, this is a fine idea. You guys get this? I haven't seen anyone say anything yet. What do you guys think about this? Does this make sense to you? All right, so yeah, most people seem to get this. Good. It's a bit weird, but it's just, yeah, that's how it works. So the next idea is kilowatt hours. Now, kilowatt hours, or kWh, also we always refer to electromotive force. We don't always, but I use as EMF. EMF is just the fast way to say it. It just means the, and again, as I said, EMF just means the voltage of the battery. Now, I don't love teaching kilowatt hours, but I think that I always tell this story when I teach kilowatt hours. The first time I ever taught kilowatt hours, I completely stuffed it up. I left the students so confused at the end of the lesson that they were begging me to go back over it. And I was like, I felt really, really guilty. What I love about being a teacher is as the years have gone on, I've gotten better at it. And so now I can teach kilowatt hours usually without stuffing it up too much. So let's talk about what kilowatt hours are, why we care about them. Kilowatt hours is another unit of energy, like joules. Okay, that's the first thing you need to understand. Unlike EMF, which is, I guess, this is not a new unit. This is not a new idea. This is not a new unit. This is just the same things that we've talked about before. We've talked about energy before. So this is just energy. It's just joules. Okay. It comes from this equation E equals PT. But the difference is that usually in power, and of course, if you're not sure, if you're like, I don't know where this formula has come from, remember we said initially that power was equal to the energy emitted over a certain amount of time. So if I rearrange that formula, I can get E equals PT. Now, the difference though is that instead of using power, which the usual standard units that we would use would be watts, we don't use watts, we use kilowatts. And for time, the usual unit we would use, actually, you know what, I'm going to ask you guys, what's the unit that we would normally use for time? We normally use watts for power, or what's the unit that we should use for time? More than welcome to say it out loud. Seconds. So thank you for clear. Yeah, seconds. But we don't use seconds here. Instead of using seconds, which is the thing we would normally use, we use hours instead. So we're replacing watts with kilowatts and seconds for hours. Now, how does this work? So 1 kilowatt hour is the amount of energy a 1 kilowatt or 1,000 watt device would use in an hour. So let's just say that you've got a good example might be a TV. The TV is about 1 kilowatt. The amount of energy that a TV uses in an hour is 1 kilowatt hour. Now, why do we use 1 kilowatt hours instead of joules? Like, we've got a perfectly good unit for energy. Why would we use this random kilowatt idea? I guess the main idea is it's a very easy way for people to link these ideas with energy to, specifically, this picture on the right is a bill, an electricity bill. If you look through this electricity bill, you will see a very, very, very small line here. Average daily usage is I think, I can't even read that even on my own screen, 50.75 kilowatt hours. I can't even read that on my own screen. I might even have that wrong. That means that, oopsie. That means that 13.75. Thanks, Calvin. 13.75. Sorry. So that means that they use 13.7 kilowatt hours per day. And you might say, okay, that's not very useful. But then you could start to be like, okay, how did they get to 13.7 kilowatt hours? You might say, well, a fridge uses 100 watts per hour. So over a day, that's going to use, 1.2 kilowatts. So therefore, you can see, you can then see, well, there's 1.2, and then you can maybe go, okay, well, maybe you've got your heating on, maybe you've got your maybe you've got your TV. You can start to go, oh, I can use this 13.75 kilowatts to easily figure out. You can probably say you've probably got about 13, about 13 100-watt devices on, or maybe you're running a 500-watt device for 2 hours or something like that. You can easily break down your electricity spending using this way to talk about energy. So that's why people use it. It's easy to go like that. Now, if I had have said, oh, you've released whatever, like 10 billion joules, well, it'd be a bit harder. You'd be like, well, how much joules does a fridge use in an hour, and how much joules does a fridge use? Whereas 100 watts is easy to go, oh, well, therefore I can easily go from 100 watts per an hour to 1.2 watts in 12 hours, so on and so forth. And you can then divide it and figure it out from there. So let's look a little bit now at how we calculate these things. First, if we know that kilowatt hours are just like joules, they're the same unit, just like how there's a conversion from meters to centimeters that are both units of distance, from seconds to hours that are both units of time, there must be a conversion from kilowatt hours to joules. And there is. Just so that we know that there is a conversion, I wanted to show you that 1 kilowatt hour, right, we're going to break this down into parts. 1 kilowatt is 1,000 watts. And 1,000 watts is the same as 1,000 joules per second. Okay? 1 hour is 60 minutes times 60 seconds is 3,600 seconds. So 1 kilowatt hour is 1,000 watts or 1,000 joules per second. How much of that is spent in 3,600 seconds? And the answer comes out to be 3,600,000 joules. So that means is that if you want to go from kilowatt hours to joules, you need to multiply by 3.6 times 10 to the power 6. If you want to go from joules back to kilowatt hours, you've got to divide by 3.6 times 10 to the 6. So that's just a conversion. Now, it's very rare that you'll be asked to convert from one to another. And in fact, when I talk about joules and kilowatt hours, I actually find that there's an easier way of dealing with joules and kilowatt hours without having to remember that it's 3.6 times 10 to the 6. If you want to write that down, sure, by all means, but I would forget it because I always forget these things. But maybe you will remember it. How do I do it then? An Xbox delivers 200 watts. watts. Oh, whoops, there's a pencil here. Ignore this pencil, sorry. An Xbox, because obviously I use that in my other lessons. For my younger year levels, you guys I don't use pencils with, you guys have got a brain of your own. And whether you want to copy this down is up to you. An Xbox uses 200 watts when in use. If it runs for 2.5 hours, how much does it deliver in joules and kilowatt hours? Now I can work out one of these and then convert it, but that is not how I'm going to do it. I'm going to do two calculations. I'm going to be doing one in joules, and I'm going to do one in kilowatt hours. So let's go. Joules. How much energy? Okay, E equals, and it's given us a power, and it gives us a time. Energy equals power times time. Beautiful. Okay, the power, 200 watts. The time, 2.5 hours. Crap, 2.5 hours is supposed to be in seconds. 2.5 hours times 60 minutes times 60 seconds is going to give us 2.5 times 60 times 60 gives us 9,000 seconds. So we've got 200 times 9,000. 200 watts times 9,000 seconds gives us 1.8 million, or 1/800,000 joules. All right. Good. Now, I could convert that, but instead I'm just going to redo it over here. Kilowatt hours. I'm going to just redo the same calculation. E equals PT. This time the power I'm not going to write down as 200 watts, because 200 watts is equal to 0.2 kilowatts. So I'm going to write 0.2. The hours, well, we've got 2.5 hours, kilowatt hours, so I have to write this down as 2.5. 0.2 times 2.5 will give us 0.5 kilowatt hours. Now, if you want, you can then convert, well, you can actually pretty easily see if I multiply this by 3.6 million, we're asking, well, what's half of 3.6 million? Half of 3.6 is 1.8. Actually, that looks like it's going to work quite nicely. So that's how I personally calculate these things. I break them up into those two parts, joules and kilowatt hours. Now, we'll do one more example down the bottom because I want to make sure that you guys get this. Let's go back to red. Firstly, a 800-watt toaster is on for 3 minutes. How much energy is delivered in joules and in kilowatt hours? Okay, start off with joules. Joules equals E equals PT. It's at 800 watts, so I can just write 800 here. 3 minutes, though, is not in seconds. So 3 times 60 is 180 seconds. 800 times 180 is 144,000 joules. 144,000 joules. Now, if I want to do this instead in kilowatt hours, I can do that quite easily by going E equals PT. P in this case, 800 watts is going to be 0.8 kilowatts. So 0.8. Ooh, time is 3 minutes. That's going to be a bit challenging. So how much of an hour is 3 minutes? To work that out, three divided by 60, which is going to be roughly 1/20. Not roughly, exactly 1/20. So 0.8 times 1 over 20. This is going to be very small. Gives me 0.04 kilowatt hours. Now, if I was, sorry, that should be, how do you do that? I think it's like a lowercase k, an uppercase W, and then a lowercase h. Doesn't matter, but I always get those confused. Now, again, you could just convert the joules into kilowatt hours. If you want to do that, fine. I don't care. But I like doing it this way. And the reason you might be like, why would you waste so much time, is because ultimately I struggled to understand what a kilowatt hour when I first started to do physics. I was like, what are these things? And ultimately, when I started to teach it using this method, it made a lot more sense to me. Oh, kilowatt hours, it's the same formula. You're just using different units. So therefore, you'll still get a unit of energy. It's just in different units. Why do we use those different units? Because they're really easy to then use to compare to a household bill. You can then really easily say, okay, well, how much energy does a house use? The average house uses about, I think it's like your average house in a day uses about 10 kilowatts. So you can be like, okay, cool. You can then get an idea of how much energy a city block has. Okay, so, you can be like, okay, so if one house uses 10 kilowatts, 10 kilowatt hours per day, then if you have 10 houses, then you've got 100 kilowatt hours per day. And so then you might be able to start doing some maths. You might be able to say, okay, well then what kind of power plant do I need to use? Also, if you then start watching sci-fi films and they're like, oh my God, this laser shoots out a 10 kilowatt, laser beam, you should start to think to yourself as like, okay, 10 kilowatts, so it's emitting all the energy a house emits in a day in a second. Well, that's a lot of energy. You can start to really appreciate these random numbers that they pull out. One last example. A fridge uses 1.8 kilowatt hours in a full day, okay, 24 hours. What is the power rating of the fridge? Exactly the same sort of stuff. You know what? I'm going to give you guys a second to work this out. I want you guys to see if you can figure this out and put your answer in chat or say it out loud, and then I'll go through it and check to see if you got the right. Check to see if you got the right answer. So work this out on a piece of paper. I'm going to open up chat. I'm going to see who gets the answer first. My bet's on Kelvin. Kelvin usually gets this first. Is that your guess already, Kelvin? 0.05? Was that for the previous one? I don't know. Who's got an answer? 2 times 10 to the negative 5. I don't think that's the answer. In fact, I know it's not the answer. I just got the answer myself. 75 watts. Yeah, that looks like the answer to me. Let's look at this. E equals PT. Right, cool. We've got 1.8 kilowatt hours. Okay, remember, it's a measure of energy, so I can just write it in. The power, we don't know what the power is, but the time we do know is 24 hours times 24. The power is 1.8 divided by 24, which comes out to be 0.075. Now, because we used kilowatt hours and we used hours, this has to end up being kilowatts, or as Foucault put it, 75 watts. Well, I just like 75 watts. And that's the answer here. If you didn't get that, that's fine, but that's how you can work out. That's just a different way of calculating something. That's just manipulating that formula. So The last idea I'm going to talk about today, oh shit, I'm running out of time. Here we go, is resistance. If I run out of time, that's okay, but there's only got 2 slides left, I think. Okay, I got a couple of slides. Maybe I won't get through all of it. Let's talk about this. Let me see. Yeah, I'm going to run out of time. I'm just going to leave it. What I'm going to ask you guys to do instead, so I guess we completely did not do the whole point of the lesson, which is lesson 27, resistance. But that's okay. What I did do is I wanted to explain these 2 ideas, electromotive force and kilowatt hours. Okay? And now that I've explained those 2 main concepts, I'm pretty confident. So we're just going to talk about resistance tomorrow, and we're going to link resistance to the Ohm's law. So that's what we'll do tomorrow on Tuesday. What I will ask you though to do is this. What I want you guys to try and work on now, it's only a short lesson, is and maybe not now, but as homework, is the Edrolo potential difference.